So we can figure out what this velocity is when our ball rolls down the edge of the inclined plane before it starts to execute projectile motion. Okay, but in order to do that, we need to know a little bit something about the acceleration of the ball as it's going down the incline. Okay, so here I've got the incline. I've redrawn it right here. I've got an angle theta in here. We'll call that angle, we'll take that angle to be 59.8 degrees. Okay, so we want to figure out what is the acceleration of our ball down the plane. All that we know is this angle right here, 59.8 degrees. So we can figure out what is the acceleration of this ball as it's going down the plane. So we're going to find what we call the parallel acceleration. The acceleration of this ball parallel to this inclined plane. Okay, so to help us here, I'm going to draw a little coordinate system with respect to my plane here. I'm going to call perpendicular to the plane, or 90 degrees to the plane, I'm going to call this the perpendicular direction. Okay, and so perpendicular you can represent as a sign that looks like this, kind of like an upside down T. That means perpendicular, perpendicular. Okay, and then the part of my coordinate system that's parallel to the plane, I'm going to call parallel. And to represent parallel, sometimes I use two bars. Parallel. Okay, so we've got a component along the plane that's perpendicular to it and that's parallel to it. And so what we're going to find is the parallel acceleration, the acceleration of my ball as it's moving parallel to this inclined plane. The acceleration due to gravity that's acting on this ball right here. So the acceleration due to gravity is straight down. But we want to talk about the components of this acceleration parallel to the plane and perpendicular to the plane in this new perpendicular parallel coordinate system. So I want to break up the components of my acceleration due to gravity into this parallel and perpendicular component to the plane. So here, my ball, if I go straight this way along the perpendicular axis, this is what I'll call a perpendicular. Okay, and then this component right here of my acceleration vector, acceleration due to gravity vector, I'm going to call this component a parallel. The component of my acceleration due to gravity parallel to the plane. So essentially what we're doing is finding the acceleration due to gravity acting on this ball that's parallel to this inclined plane. Now I'm not going to go through the proof here, but if this angle down here of my inclined plane is 59.8 degrees, then this angle here that you see of this little right angle triangle that I drew is also the same. I'll just still call it theta. Okay, it's still equal to 59.8 degrees. So I can figure out this acceleration parallel to the plane by using trigonometry. Okay, and so the parallel side is opposite of this angle right here. So sine theta is equal to parallel component of my acceleration down the plane over the hypotenuse of this little right angle triangle here, which is the magnitude, okay, of our acceleration due to gravity. So then the component of my acceleration along the plane is equal to our acceleration due to gravity, the magnitude of that, times sine of the angle of this incline. So the acceleration that you're going to look for is 9.8 meters per second squared sine of our angle 59.8 degrees. Okay, so when I put the bars around it, that means you take the absolute value. So this number is just positive 9.8 meters per second squared now. So then my acceleration of my ball down the plane is equal to 9.8 times sine 59.8, which is 8.47 meters per second squared. So it's not quite accelerating down the plane at 9.8 meters per second squared like it is in free fall. It's just a little bit smaller than that because we're on an incline with respect to the horizontal. So that's the answer to the question for what is the acceleration of this object down the tilted plane.